Good morning. Good morning. Welcome. Let's get started, shall we? Yes. Good morning and welcome to Robotic Science and Systems here in Pittsburgh, hosted at CMU. My name is Nathan Michael. I'm local arrangements chair, and this is Hadas Kreskazit.
Nice.
Yes. Program chair. And so we're very excited to have you here. It's a great pleasure and honor to have all of you come. Thank you for coming. We just wanted to welcome everyone before we started the first session. This year we're doing a few new things. For one, you'll see that we have live captioning on the bottom of the screen. We're also doing live streaming, so welcome to everyone who is joining remotely at this time. And the live streaming information is available on the website. We have a very exciting program with many, many exciting and interesting talks, as well as evening events. You should have received in your registration bag or your bags the program itself, and this is also available online. In terms of evening events, we this evening have an industry reception as well as a panel discussion that will be held here, and there will be heavy hors d'oeuvres. So please join us this evening for that event. Tomorrow evening, we will be holding a Pittsburgh Robotics Showcase, Robotics Institute open house, as well as tours of NREC and Uber ATG, and these will be occurring at the Robotics Institute at Carnegie Mellon University. And then Thursday evening, we have the banquet at the Heinz History Center. And so this promises to be a very exciting conference. Thank you very much for coming. Let's get started.
Everyone, thanks for coming for the first session, the first day. Thanks for waking up early, even if you're jet lagged. First of all, let me say just very briefly what a great privilege to be in this magnificent room. Like, I don't know if you've taken a chance to look around, but I think it's a great honor to be able to use this room for what we're doing here today. It's a music hall, right? So in theory, can you hear me? Like, it's supposed to have really good acoustics, right? Anyway, but we're using mics. We like technology. So I'm just going to go ahead. We have 30 minutes for talks and then Q&A, which is going to be shared by all the speakers. So the first speaker is Douglas Morrison. He's going to talk about manipulation. All talks in this session have to do with manipulation and contact. And the first one is closing the loop for robotic grasping, a real-time generative grasp synthesis approach. So if you can please come to the podium. And now I've been told that I have to look for where the videos are. Okay. There's a 5 here, so that probably is not the right session. There's a 1 here. That's good.
Yeah, 1.
It's that one, right?
Yep, that one right there.
All right.
Perfect.
Thank you. So you have a mic. So I want to press play. You know you have 5 minutes, and you're going to have to sync. 3, 2, 1, go.
Thanks. I'm Doug Morrison from the Australian Centre for Robotic Vision, and I'm going to be presenting my paper, Closing the Loop for Robotic Grasping. In the last few years, there's been a large number of deep learning approaches to robotic grasp synthesis. And while there's a wide amount of different techniques that have been used, a lot of them actually share a very similar pipeline. Given an input image, a sampling algorithm, such as sliding window, is used to generate hundreds or thousands of grasp candidates. These are then ranked individually, normally using a deep neural network, and then they're executed open loop. Generally speaking, this is quite a slow process, in a lot of cases taking a second or more to compute, which means a lot of these techniques rely on having a completely static environment, as well as very precise calibration between the robot and the environment. So in contrast, we present a different approach to robotic grasp synthesis. We generate a one-to-one pixel-wise distribution of grasps given an input depth image, which we call the grasp map. The grasp map describes at every pixel the quality of a grasp at that pixel, the rotation angle for a 2-finger grasp, and the grasp width at that pixel. And we do this in real time. using a relatively small convolutional neural network. And so this allows us to use our approach inside a closed-loop controller, which means that our approach is able to handle moving objects and also react to imprecise robot control. A second advantage to our non-sampling approach is that we're not limited to a discrete set of grasps as would be generated by a sampling approach. Instead, we can just query the grasp map at any point. So for example, we could just take the single best grasp that we've detected and execute that. We could take the local maxima of the grasp map and rank them by some other task-specific heuristic. Or we can just sample the grasp map at any point to determine the best grasp at any point on an object. To generate the grasp map, we use a relatively small, fully convolutional neural network. It takes a depth image as an input and outputs what we call the grasp map as an output. And so for each pixel, this describes the grasp quality, the grasp width, and the grasp angle. You can see an example here of our system generating the grasp map in real time for this moving object, with the pose and rotation of the best detected grasp for each frame shown on the right. To train our network, we generate a data set of several thousand ground truth grasp examples by augmenting the Cornell grasping data set. The Cornell grasping data set contains several hundred hand-labeled images with grasps, and while it isn't the largest grasping data set available, it allows us to very easily generate the pixel-wise grasp maps that we require for our training set. For our experiments, we implement a relatively simple pose-based visual servoing controller with our grasp detection system in the loop. And we track the best frame by generating velocity commands at each time step. For our first experiment, we attempt to grasp singulated objects which are moved during the grasp attempt, randomly by at least a specified amount. We attempt to grasp two different object sets. Firstly, a set of 8 3D printed objects with complex and adversarial geometry, as well as 12 household objects, which have been chosen from standard grasping data sets, the YCB and ACRV grasping data sets. You can see an example of one of these grasps here, if it hasn't been cut off too much, of grasping a moving object which we're able to track in real time. Secondly, we show that our system's able to generalize to cluttered environments. We use the same experimental setup as before, where the objects are moved randomly after the grasp attempt has started, and in this case, the robot's required to grasp each object until they've all been cleared from the table. And finally, we highlight another advantage of our approach, which is the ability to account for imprecise robot control. We do this by simulating a kinematic error in our robot by introducing a cross-correlation between the velocities output by our controller. And unsurprisingly, we show we're able to outperform an open-loop controller under the same set of error conditions. And finally, I'd just like to note that all of our code and train network are available on GitHub, and we strongly encourage anyone who's interested to use and improve on our system. Thanks very much, and if you have any questions, please don't hesitate to get in contact or come see me at the poster session this afternoon. Thanks.
The next speaker is going to be Chris Hauser, who's a solo paper Bayesian tactile exploration for complaint docking with uncertain shapes.
Thank you, Alberto. Let's see. Do you have to click something?
Yes, you see? All right. You can double click if you want.
All right, here we go. All right, everyone. Thank you for coming up so early to listen to my talk. My name is Chris Hauser. I'm from Duke University, and today I'll be talking to you about an approach to a problem that I like to call docking. This problem is to try to take some kind of end effector of a robot, we're interested in rock climbing in particular, and to place it securely against a surface or an object. This is something that we are working on with this RoboSimian robot, and one of the interesting things about rock climbing, both as a human and a robot, is that as you're trying to find good holds to climb, the view that you have towards the interesting features of the terrain are occluded. So for example, cracks or ledges cannot be seen directly from your point of view. And it's really important to find secure handholds through the sense of touch because you can't see them directly. If you can't find a secure handhold, you have bad results. So our approach to this problem, so actually there's been a lot of related work in tactile exploration. Tactile information has been used to acquire object identities and locations. It has also been used to acquire object shape. So it's also been used to acquire friction as well as terrain shape simultaneously. Now this work that we propose is a task-oriented tactile exploration process, which means that the exploration is used to try to accomplish a single task, which in this case is to do docking. But other people have done task-oriented tactile exploration for grasping and so on. But for this paper, we contribute Bayesian estimation and probabilistic simulation techniques that allow us to scale to high-dimensional shape distributions. So the general approach is a loop where we first take a prior model of the probability distribution of the shape. We then plan a compliant motion to maximize the docking probability. We execute the plan, and then we estimate the posterior distribution over terrain shapes given that information. There's so two contributions here. One is the Hamilton-Monte Carlo method for sampling these posterior distributions, and the second is a probabilistic compliance simulation technique that's able to account for sticking, sliding, friction, as well as free segments. So for the first contribution, this is a technique to try to sample from the posterior given information from path execution. So when your path has either cleared out free space or has stuck or slid, you want to find the posterior from that. We present a Hamilton-Monte Carlo method that's able to sample this more efficiently than other comparative Monte Carlo techniques, rejection sampling, Metropolis Hastings, and Gibbs sampling. This uses a particle momentum technique and a constraint bouncing technique in order to achieve its efficiency. Once we have this technique, we're able to then put it into a planner. So we have a probabilistic model of shape. And after that, what we do is we have a planner that requires to estimate this docking probability. This needs to be done a lot of times in the planner. And so one of the things that we did to speed this up was to give an analytical treatment of simulation under uncertain shapes. So here, the idea is that you have a certain motion that you want to execute. And so what we do is we estimate the probability that you hit each edge in your shape. Then you estimate each probability of sliding to the left and sliding to the right onto each subsequent feature. Now you repeat this for all possible edges, both to the left and to the right of the kind of most likely edge. And then you can sum this up, basically can solve this problem in order n time for a given docking path. And so we can estimate very quickly the probability of docking at any given site. So with this technique, we compared it against a couple of other heuristic approaches. One is to first dock at the most likely docking site and then try to explore around it. Another one is to perform information gain alternated with greedy exploration. And compared to both Bayesian tactile exploration, it focuses its actions more precisely on the task at hand. And so it's able to acquire docking sites with very few cycles. We did some experiments in simulation. This is the RoboSimian robot simulated with a compliant controller and a noisy sensor. Most of the time, it's able to acquire good docking sites on the first try, but the more interesting cases are when it actually fails. So in this case, it actually tries to acquire the first hold, but due to localization errors, it ends up hitting it from the underneath. And then what it does to account for that error is that it finds a new docking site down lower on this second hold. And then it successfully docks. We have some other interesting failure cases because this is a stochastic kind of technique. There's a lot of things that you can't really predict. So one thing that might come up is that your sensor might give you a false positive and show something that looks like a really good hold. So in this case, the robot tries to grab onto this piece of noise, and then it ends up slipping, and then it plans a path to actually the lower hold again. It's back up, but it ends up hitting a good hold by accident. If you want more information, I'd be happy to talk to you about this at the poster. Thank you.
Thanks, Chris. The next talk is by Florent Lamigo, handling implicit and explicit constraints in manipulation planning. So you can double click, and I'm going to try to.
Good morning.
My name is Florent Lamiro, and I come from Toulouse in France, where I work in Atlas. So we want to design algorithm to solve manipulation planning problems like this one, where two robots manipulate and assemble objects, several objects. Along manipulation path, configurations are subject to numerical constraints that can be implicit. For instance, a quasi-static equilibrium of a legged robot, or holding an object with two hands, because you have a closed loop. Constraints can also be explicit. When a robot grasps an object, then the position of the object depends on the position of the robot, of course. And solving numerical constraints is thus at the core of manipulation planning. So manipulation paths are continuous curves in the composite configuration space of the system. The composite configuration space is the Cartesian product of the robot and object configuration spaces. And the configuration of objects are represented by 7 numbers, 3 for translation, and 4 that stand for a unit quaternion. An explicit constraint is a constraint where some configuration variables depend on others, like when an object is grasped by a gripper or lies on a table. An implicit constraint is defined by a vector-valued differential function G1 that should be equal to 0. Combining several explicit constraints may result by substitution to an implicit system of equations on a reduced set of variables. For instance, if the same object is held by 2 robots, the position of the object depends on the position of the robots, and there is an implicit constraint linking the position of the 2 robots. Note that the unknown of the implicit constraint is a reduced set of configurations because the variables of the object have disappeared. To solve an implicit constraint, we use Newton-Raphson algorithm. First, we linearize the constraint around an initial guess Q0. Then we solve the linearized constraint to get another configuration Q1. Plus here denotes the pseudo-inverse of the Jacobian of the constraint. We linearize and solve again around Q1 and stop when the norm of f of q is small enough or when a maximal number of iterations is reached. The paper explains how to handle several constraints in order to generate, by substitution, a set of explicit constraints and a vector-valued implicit constraint on a reduced set of variables. The paper also explains how to compute the Jacobian of the remaining implicit constraint. In our implementation, constraint paths are defined by a path and a constraint. To evaluate the configuration along a constraint path, we first interpolate, and then we solve the path constraint. In this example of an arm holding a disk, the interpolation between 2 configurations yield the intermediate configuration for the arm and the blue position of the object. After applying the constraint, we get the configuration where the object is in green in the gripper. So manipulation planning mainly consists in generating constraint paths. And in this work, paths are thus not discretized, which is very important. All this work is integrated in an open source software platform called Humanoid Path Planner that helps defining and solving manipulation planning problems. A problem is defined by some robots, some objects, and a set of possible grasps, an initial and a final configuration. Implementing dedicated algorithm is very easy using this platform. Like you can see this one, for instance, where a humanoid robot manipulates an object with 1 or 2 hands. Thank you.
Thank you, Floren. The next speaker is Maximilian Hasshager. He's going to talk about passive static equilibrium with frictional contacts and application to grasp stability analysis. And that one, you can double click.
Good morning, everybody. Also to those watching the live stream, thank you all for being here. We're a group that's interested in grasp stability analysis. So the question we'd like to answer is, will a given grasp resist a given disturbance? And the reason an answer to this question is important is, for example, for grasp quality metrics, which is a way of telling how good a given grasp is. And those, in turn, are important for grasp planning. So all of these issues are very much foundational to robotic manipulation. So there are many different approaches to grasp stability analysis, but none of them make what we believe is a key distinction, and that's between active and passive resistance. So let me just describe what we mean by this distinction with this example grasp. We have an object being held in a very primitive robotic gripper and 3 contacts. At every contact, we have friction cones, and those define the space of contact forces that satisfy our friction laws. Now, we intuitively know that if we push this object down into the grasp, we can push arbitrarily hard, and this grasp will remain stable. Of course, if you push too hard, you'll be breaking the hands, but up to that, it's stable. We also know that if we pull this object up, it'll be sliding out of this grasp unless we load contacts 1 and 3 sufficiently such that friction forces at those contacts can keep the object in place. So what that means is that there are some disturbances that this grasp will just resist purely passively, and then others require some sort of active input, some sort of preload on the grasp. And that's important because what we tend to do in practice with robotic hands is that we command them to close around an object, and then we keep the commanded torques the same throughout the task. So really, the question we should be answering is a given grasp with a given preload stable with respect to a given disturbance? So let's formalize what we mean by passive stability. Passive stability means that there are contact forces that balance the disturbance that's applied to the object. Those contact forces obey some sort of friction law, and this can be something as simple as a Coulomb model. And then finally, those contact forces must obey energy conservation laws. And in this specific case, what that means is that friction forces must obey by the maximum dissipation principle. This principle states that friction forces must dissipate as much energy as possible, which means that they must oppose any incipient motion on the object. And that's something that's very difficult to solve for because a contact can either stick or slip. This means that at each contact, the frictional behavior will be radically different depending on if the contact is stationary or if there is some sort of tangential relative motion. And it turns out this is actually a non-convex constraint, which makes it very, very difficult to solve. So what we present is an algorithm that solves the passive equilibrium problem in 2 dimensions, and it does so in polynomial time. And another thing that's interesting about the algorithm is that it provides some strong guarantees. And that's something that practitioners don't often get in this day and age of learning and data-driven approaches. Particularly the guarantees we provide is that if there is a global solution, our algorithm will find it. And if our algorithm doesn't find a solution, then it's guaranteed that there is none. The key insight that this algorithm is founded on is that we treat each contact to either be sticking or slipping. Now, the combinatorial nature of this approach might suggest that there is an exponential number of combinations of slip states in the number of contacts. But it turns out that due to rigid body constraints, it's actually only quadratic. And that's really what our algorithm, the insight that our algorithm is founded on. So let me show you where this makes a difference. Let's consider again the grasp I introduced earlier, and let us now apply disturbance forces that lie in the plane. What we have here shaded in blue are the forces that our algorithm predicts this grasp will withstand both with and without a preload. And then what we also have here for comparison is in violet the grasp branch space for this grasp. And as you can see, our algorithm correctly predicts and captures both the ability to withstand arbitrary downward disturbances and also the necessity for a preload for any disturbance that has any upwards component. And those are both things that grasp branch space-based approaches won't capture accurately. So in conclusion, we present an algorithm that is model-based, polynomial runtime. It captures how practitioners actually use robotic hands, and it also provides some strong guarantees. Thank you very much, and I'd love to talk to you later.
Thanks, Maximilian. I'm going to ask now all speakers to come up on stage. We're still with their mics. Maximilian, come. We're going to have a short Q&A session, joint session, so if you can go in front. So you're the subject of scrutiny right now. What's that? Oh, you don't have mics anymore? Okay, so I guess you can come here whenever someone asks a question. And now is when I am forcing you to raise your voices and attack them or just compliment them. Anyone has a question? Please voice it now or
Hi. So my question is for Chris. When you have uncertainty in the measurements of the surface, how do you figure out the probabilities of sliding on an edge one way or another?
So it's, oh, let's see. Okay, so there are a lot of details. Basically, it turns out that you have an intersection of several quadratic and linear constraints that you can use to determine the conditional probabilities of sliding after you've slid off of, after you start sliding at some point on an edge. I'd love to talk to you about all the details, and it's a really, there's a lot of math in the paper that I'd love to write a larger paper about, but I'll talk to you about it later.
Okay, thanks.
Next question. Raise your hand a bit higher. Okay, I'm going to ask, oh, no, I'm not going to ask a question.
Hey, this is for the first speaker. Thanks for your talk. It was very interesting. Have you considered non-overhand grasps at all?
Yeah, it's actually something I'm working on at the moment. So we didn't go into it for this paper, but it's something we're looking at now.
And does the approach have to change a lot, or are there related techniques?
It makes it a bit more difficult, obviously, because you need to incorporate more dimensions, but the approach can stay more or less the same. You just need to take note of the angle you're looking at objects from as well.
So this is a question for Chris. Regarding your HMC algorithm, so usually these things require differentiability in the probability distributions, whereas these things are like sort of decisions between sliding, sticking, they're discrete decisions. So how do you differentiate through those?
So the HMC technique that we propose is assumes that the prior distribution is Gaussian in some super high dimensional space, but it formulates constraints corresponding to the free sticking and sliding condition that turn out to be basically feasibility constraints in this space. And so you're trying to sample from this subset, this feasible subset of this probability distribution that's in some high dimensional space, Gaussian. We formulate this in the paper. It's basically a union of several convex sets, so it's a non-convex object. There's a constraint bouncing technique where you kind of analytically figure out there's ellipses in which the state space travels on, and then you try to find the first point at which you hit the feasible set boundary, and then you bounce off of that boundary, and show how to do that in the paper. And I'd love to talk to you more about this.
I think we have time for a couple more questions. Do we? Maybe one? Okay, I can ask a question while you think on about the next one. This is for Maximilian. It's great that you guys found a polynomial time algorithm to prove equilibrium, and I'm curious about how much of that
polynomial relies on the fact that these are point contacts, and if there's any hope to generalize to, I don't know, patch contacts or any other kind of like soft contacts, for example.
So soft contacts, I mean, you can well, this isn't working, all right. So I believe you can approximate a patch contact by multiple contacts, and then in that case, our method would still very much work. And that's actually something where it would work very well because of this rigid body constraint that we use, cutting down the number of possible slip states. Contacts that are like close to each other will be very constrained that they can't have many different slip states all at the same time. So as long as you approximate with multiple point contacts, this method will still work.
Anyone else? No? Okay, I have another question here. Oh, is there a question? No. Maybe? No. Anyway, so I have another question for Florent. This might be a bit more contentious. So you said something in your talk, and I want to get your reaction, and maybe the reaction of the audience. You said, and I think I'm quoting, manipulation planning, thus, is all about solving numerical constraints. I just wanted to sort of give you another chance to sort of elaborate on what that means, or see if anyone else has an opinion on that.
Okay. Can you hear me? Does it work?
I think it works.
When you do classical motion planning, you have to search in a whole space. You can use all the variables. In manipulation planning, you cannot move in any direction in space. You are always constrained by some constraints. So you may have different states. For instance, one state is when I hold the micro with my right hand. Another state is when I hold it with my left hand. And then you have the intersection of the two, which is another state. So you have to explore in those states that are represented by foliation of the configuration space. So that's why I said that numerical constraint is at the core of manipulation planning.
Okay. Cool. Anyone else? No? Okay, so I guess no one else. Thank you very much, everyone. If we can just thank the speakers once again.